Now in Calculus 2, we found the arc length for rectangular functions where y was a function of x, for polar functions where r was a function of theta, and for parametric equations where x and y were both functions of t. So of course now we want to find the arc length for vector valued functions. So I'll go through a quick derivation of that formula without a lot of technical details, but similar to what we did back in Calculus 2. And so if we take a curve, a smooth curve, and we want to find the length from A to B, we think of partitioning the A to B into segments and approximating the straight line between the two dots by finding the change in x, the change in y, and using the Pythagorean theorem. And we want to add up all of those to find the arc length. Now, some of the relationships in vector-valued functions create an interesting formula for arc length and a pretty simple one. If we take the function, two-dimensional function, r, and we've done this recently, the magnitude of r is the square root of the sum of the squares of the individual components. Well, if we do that same thing with the derivative, you notice what we get is exactly what we just found for arc length. So the formula for arc length in vector valued functions can be written simply as the integral of the magnitude of the derivative of r. And it's nice and interesting because it is the exact same formula in 3 dimensions as it is in 2 dimensions. Now here's a typical problem where we're asked to find the length of the curve between 2 points on the curve. Well, first recognize that since the third component is t, the third component of the first point indicates to us that t equals 0 is our beginning, and the third component of the second point implies that t equals 2 pi is our ending. So we'll want to be doing the integral from 0 to 2 pi. Now we'll do the derivative of r. We'll do the magnitude of that. Simplify. And then integrate that from 0 to 2 pi. Now that's not too bad of an integral to do. And as you can probably guess, this is very easy to program into the TI-89. Now, from the formula for arc length, we can write the arc length function. Now, in the arc length function, notice here we have s as a function of t, and the variable t appears as the upper limit of the integral. Now, we studied these sorts of integrals in Calculus 2. We call these functions defined as integrals, where the actual variable of the function is the limit on the integral. And if you remember, what we did was we used a different letter here than our variable, and we called it a dummy variable, meaning we're not really interested in what that variable is. We're interested in the s and the t. As long as that other variable's not a s or a t, we're in good shape. Now, this is a function that represents the length of the curve between the r of a and r of t, meaning any value of t, a meaning some constant. Now, we did this in Calculus 2. One of the only things that we did with functions defined as integrals in Calculus 2. And that is the derivative of this function. Now, perhaps you'll remember this from Calculus 2, and that is when we have a function defined as an integral, the derivative of that is nothing more than the integrand with that variable. And so the derivative of s with respect to t is nothing more than the magnitude of r prime of t. Now, if that magnitude of r prime of t was a 1, then our integral of 1, if we do the fundamental theorem, would be t minus a. Now, that produces some interesting results. One of which is if a is 0, then we basically have t and s equal to each other. So the arc length would be the same as the parameter. That's kind of neat. Sometimes in science and engineering we have functions like this one that are given in terms of time, and that's why we oftentimes see the parameter t used in these functions. So the curve is being drawn, or something is following a particular path, and we're giving the position in terms of the length of time that the thing has been traveling. That's a common scenario in a lot of motion problems. However, here is a graph of this function, and I put vectors on there for t equals 0, 1, 2, and 3. And you can see the displacement, the distance, the position change from t equals 0 to t equals 1 is not the same as the position change from 1 to 2 or 2 to 3. So this thing is traveling different distances over equal periods of time. What arc length parameterization is a way of changing that so that the parameter in this case gives us equal distances. If you look at the drawing, you'll see the distance from s equals 0 to s equals 1 is the same as s equals 1 to s equals 2, which is the same as s equals 2 to s equals 3. Now that's if we change the parameters. The function that you see here, r, is exactly the same graph, the red graph, as the one we had before. It's just developed on different values of the parameter. In this case, equal values of the parameter giving equal changes in position. So the last thing we want to take a look at then is, so how do we do that? How do we change a function that is parameterized by t into a function that is parameterized by s? So from time to arc length. This is called arc length parameterization. And it goes like this. We want to simply use a different variable besides t, and then do the derivative and the magnitude, and finally do the arc length function. This is what we had earlier. We're starting at 0 simply because that's where t is starting. So we're doing the integral from 0 to t of the magnitude of r prime, that's the 5. And so that integral comes out to be a 5t. Now, if s is equal to 5t, we can solve for t to get a value that we can then substitute back into the original function.